So I think we reached that point in, yeah, I try to convince you, I don't know if I succeed, to that if we want to solve classical mechanical problems, maybe it's a good idea to try a different technique that does not rely on Newton's equation. Of course, Newton's equation is perfectly fine, and you can keep on solving problems with that, but here we want to try a different approach. Maybe easier. I mean, of course, it's more complicated at the beginning, as any new things looks a little bit complicated at the beginning because it's new, but then as you become familiar with the different approach, then you know, as you gain familiarity with this, I hope you start appreciating the advantage. And really, let me just emphasize one more time. Here, the idea is that I give you a general technique that then you apply to each and every problem, okay? So that you don't have every time to look at the problem and to discover, so to speak, a way to solve it for each problem every time. Just a general approach that you know that you crank in and solve the problem. Now, the first things that you need is to, as you've seen, I mean, you have to write some coordinates for your problem, right? Because the problem is going to be some points or some bodies in some field, and you have to describe your system, so you need coordinates, okay? How many coordinates do you need to describe the position of one point in space? Say a point here in this room, how many coordinates do you need? 3, right? Obviously. And if the points happen to be on the surface of a table, clearly you need just 2. And if it's on a line, just 1. In fact, that's what defines the number of dimensions of space, right? And usually you call those coordinates, say, x, y, and z, right? And then you can write the velocity and the accelerations that you need in Newton's equation by taking derivatives of that. In this business that we are doing, the number of independent coordinates that you need to completely determine the position of your object, okay, is called degrees of freedom. Have you ever heard about this? And you understand why. I mean, because as you fix, you start with your body that can move in any way, okay? So it has a lot of freedom. And as you start fixing these coordinates, you constrain your body step by step until it cannot move any longer because you have completely determined the position of that body, right? So that's why it's called the number of degrees of freedom. So a point particle has 3 degrees of freedom, right? And then you fix these 3 by giving the position in space of this particle, and you have completely fixed. Now, if you have n particles, so here was 1 particle. If you have a swarm of particles, say n, big N, how many degrees of freedom that system has? 3n, right? Because for each of these particles, you need 3 coordinates in order to fix the position. So in general, if you look at your systems, you remember what we did 2 days ago. I looked at my problem and I wrote some coordinates, right? And I checked that how many coordinates, for instance, how many unknowns I had, and then I gave a name of that. So now we don't want to, here I just use Cartesian coordinates, but as I said last time, I don't have to use Cartesian coordinates to describe my body. Sometimes, in fact, very often, it's more convenient to use other coordinates. So let me just call these coordinates Q sub I. So these are called generalized coordinates, okay? Because, okay, they can be Cartesian coordinates, but not necessarily. They can be, you will see, angles, you will see. They can be energy, they can be whatever. And so if I need an equal number of generalized coordinates as the degrees, the number of degrees of freedom that I have, okay? So if I have 3 degrees of freedom, in general, I will need 3 generalized coordinates to describe the system. And if I have generalized coordinates, you understand that I'm going to have an equal number of generalized velocities that I'm going to indicate just by putting the usual dot, as Newton liked to do, for the derivative, the total derivative with respect to time. So in this language, if I have completely, so those then satisfy these second order differential equations. And if at the initial time I give you all the generalized coordinates and all the generalized velocities, then the system is completely determined. And if you solve the differential equations, you will know how the system evolves in time. So, for instance, this piece of chalk, how many degrees of freedom? Of course, if you think of the piece of chalk as a collection of atoms, then you know you have the Avogadro numbers times 3. So, but it's not, right? Because in fact, it's a rigid body. The atoms here, they are not free to move whatever they want. They are constrained to keep the shape of this object. So for something like this, now try to think, maybe a good idea is to think you have a body like this. We will see that in many details further on, but it's nice to think of the center of a mass, you know that, right, of this object, right, and then the motion of the body about its center of mass. Now, to fix the center of a mass, that's a point. So you need 3 coordinates, right? But then once you have fixed the center of a mass of this, still the body, right, can rotate about the center of a mass. So I guess you need 3 more coordinates, that may be some angles there, right? So you need 6 to completely fix this, right? And then you can, well, look around you. It's a good exercise to think how many degrees of freedom the object has. Of course, all rigid bodies, they have 6, right? Because it's like the chalk. But if the body is not rigid, then you need many more. Think of myself. If I have to fix completely my position, I need a lot of coordinates, and so on and so forth. I mean, in this class, we will essentially consider either points, right, that they are nice, and then they only have 3 degrees of freedom, and then maybe some rigid bodies, then so they are all simplified systems. But bear in mind that the system can be quite complicated, and in that case you need more coordinates to completely determine all the degrees of freedom. Okay. So I have my generalized coordinates. Now I want to, as I said, I want to derive, you remember what we did last time. I wrote this combination of the kinetic energies minus the potential energy. I call it the Lagrangian. And then I pulled out from my head an equation that I call Lagrangian equation. And I show you that, at least for that case, that as far as we went, I get exactly the same equations as if I had used Newton's equation. So here I should try to derive why that equation, right, gives you exactly the same answer than Newton's law. I mean, they don't look the same. They don't deal with the same quantities, right, because one has energy and the other has forces and acceleration. But indeed, today we try to derive one from the other. Before I do that, however, I should say a few words about the constraints. Okay, constraints are those conditions that, for like here, right, like for the atoms in this piece of chalk, they keep your points at fixed positions, one with respect to the other, right? So these are constraints. A constraint is the surface of this table, because if I put something on top of that, these things can move in these directions, right? Maybe it can move up here, but it cannot go beyond the surface of the table. So this is a constraint, and I don't know, you name it. You can think of many, and usually your problem has constraints. We saw that when we draw the pictures for the 2 or 3 problems that we solved together in the previous 2 classes. A constraint, I mean, if you draw this, and I say this block has to stay on top of this other, that's a constraint, and so on and so forth. You have many constraints. Every problem is essentially defined by its own constraints. But I said that the other things I didn't like very much about Newton's second law is that each time I have to work out the constraint in order to solve the problem, right? You remember, because I had to find what n was and the t and so on. And this is not nice, because each time you have to think and you have to be clever, and you have a limited amount of cleverness that you want to use for each problem. So maybe it's nicer to get rid of those. So many constraints, you actually can get rid of them by using these generalized coordinates. And you can guess what kind of constraint. If your constraint, so you have certain number of particles, and the position of these particles, are identified. Let's stick to Cartesian coordinates for the moment. So you have n particles, right? So their positions are fixed by, this is a little r, if it's not clear. I don't know how you, or like this. I don't know. R for the position. Now, if you can, so these are all the particles, and you see a class of constraints, maybe t is there too. You have a constraint that can be written as an equation among the coordinates, okay? That's a very common case, but it's not the most general, okay? Is this clear? If I can write my constraint in this form, for instance, if I have a point particles that is constrained to move on a loop, right? On a loop. This is clearly on this form, because if I write the coordinates of these particles, right, they are linked by the fact that they must stay on the circle. So you have something like this, right? And you see this, I can always write it in this form. So is in this form here, right? So each time your, say, point particle, to consider the simplest example, has to stay on some given curve, then clearly you are in this situation, okay? Now, this kind of constraints, they are called, well, here's just a name, holonomic. That I'm not sure. Well, you can look it up. I'm not sure what's the. It must come from Greek, but I don't know exactly the meaning. So, and so for this important class of constraints, you immediately see that you can get rid of the constraint simply by picking the generalized coordinates in a clever way. Because you can solve this equation and write one of these coordinates as a function of the others, right? And so you started with a system that had n independent points, so it had 3 times n generalized coordinates. but they were not generalized coordinates independent, right? Because of the constraint, one of them can be written in terms of the others, right? It's like here. It looks like you had two coordinates, but actually, once you have given x, y is just a function of your x, right? So you only need one generalized coordinate to describe the system. So that's why this class of system, this class of constraints got a special name, because if you have your constraint in that form, then you know that you don't have to worry about the constraint, because as long as you write your system using generalized coordinates that are independent, the constraint is built in the coordinates. Is this clear? Like here, if I write all my equations in terms of just x, right, and I don't consider y as an independent variable, then I don't have to worry. I can forget about the constraints because it's built in the fact that I'm using those coordinates.
What does a t represent
T?
in that?
Time. So I'm assuming that this is an equation that depends on the particle's coordinate, but maybe also explicitly on time.
So this equation you are writing here.
Well, no, this is a special case in which there is no time. I mean, the fact that I write it here doesn't mean that it has to appear every time.
So that is the FR1 is a constant. The whole of that equation is a constant.
This is the constraint. Yeah, my f in this case is this. So it's just a special, very simple example. But you can think of it as, for instance, you have your particles here, and is constrained to slide on this stick. But now think the stick is rotating with some angular velocity. Now you see that the position of this depends explicitly on time, right? Because the angle here is going to depend on what time you measure, and it still is a constraint on this form. Okay. Of course, the rigid body, as I said, is a special example of this, because if you look at this, you can define the relative positions of all these points, right? And because it's a rigid body, that means that the distances between two of these, say I call R sub I, R sub J, I take 2 points in this rigid body, their relative distance is constant. That's why it's called a rigid body. So the rigid body is a particular case of this holonomic constraint, and of course it's an important case. Maybe I should take a square. And that's why the rigid body has only 6 degrees of freedom, right? It doesn't have 3 times the Avogadro number, because all those atoms are somehow fixed. The distances between 2 of them, just to remain in the rigid body, are fixed. So instead of having this Avogadro number, 10 to the 23 or whatever, you only have 6. So, and as I said, if you identify those 6 coordinates like I did before, center of mass plus rotational, then you can forget about the rigid body. Just write your equations for these 6 coordinates, and the constraint is taken care automatically. So you may wonder, okay, this is the holonomic, but what is an example of non-holonomic constraint, right? Because it looks like everything is holonomic. No. In fact, for instance, this table is not a holonomic constraint, because it is not in the form something equal, right? Rather is in the form something larger than this plane, right? If you introduce in this room this plane, the constraint is that the position of this, so a function of this coordinate, can be anything except it can never be smaller than the table. So it's in this form, and this form is not holonomic because you see you cannot solve one of these coordinates as a function of the others because you have a greater than instead of an equal, and that cannot be solved to get rid of one coordinate. So that's an example of non-holonomic constraint. A famous example of non-holonomic constraints are the walls. For instance, this room, there is air, right? I assume, otherwise we will not breathe. And most of this cannot escape, right, because of the side walls. And this is another example of non-holonomic constraints, because this little molecule of oxygen can go everywhere until it hits the side here, right? But this is not in the form of something equal. Again, if something has to be less or greater than this value here, okay? So how about if you have a disk, right, that is rolling on a plane? So it's following some, okay. So it's a disk and it's rolling on this plane, some plane given like this, okay. First of all, how many coordinates do you need to fix this system? So how many degrees of freedom do you have? Is that 6? Let's see. First, you have to fix the position of this disk, right, in this plane. So let's say you have 2 coordinates like this, right? So with this, you can fix this point here that is the point at which the disk touches the plane, right? And then you have to specify also, I mean, the rotational state of this. So you need another coordinate there, right? Is that enough? You sure? So it's a disk. So, okay, 2 coordinates to decide where in this room is the center of mass, if you wish, or the point at which it's touching. Then I said the rotation, right? But then it could also, right? Is that clear? I mean, it rotates like this, but it can also rotate, say, about this other big axis. So there too you have another angle. So it seems to me that you have four degrees of freedom. Now, usually when, have you seen this kind of problem in your previous life? You must have solved some problems like this, a rolling disk. And usually, if you remember, or if you don't, I'll tell you, by rolling, I mean that the disk is rolling without slipping. You see the difference, right? I mean, something is rolling if this point never slips. This is not the usual case. If you are on a bicycle, sometimes, especially if it's wet, the rolling is not perfect and you slip, like, you know, it slides. And what is the condition for this ideal no slippage rolling is that the velocity, so this disk has some velocity in this direction, and of course it has a rotational velocity, you know, because it's just going around. So if the radius is a, and I call it phi, I have a phi dot, right? That is the velocity of the disk about the center must match exactly the velocity along the plane. So this must be exactly equal to v. In this case, you have rolling without slippage. If these two velocities mismatch, is when with your bike you are braking very suddenly and then you are slipping, right? Very dangerous, especially if it's wet. So usually in the problems that are given, because they want to help the students, they only assume that the system is rolling without any slippage, okay? Because otherwise it's very complicated. So if I say now that this disk is rolling on this plane, I'm giving you a constraint. Because you see, I'm connected. You see, v in this case is going to be x dot plus y dot, right? If I call the position here x in terms of Cartesian coordinates. So it looks like I'm connecting your, you had 4 coordinates, but one seems to be connected to the others. But look, it's not holonomic, right? Because it's not the coordinates, but the velocities that I'm connecting. So this is another interesting example of something that it is a constraint, but is not holonomic, okay? Because the relation that I'm giving you is not on the coordinates, but rather on the velocities, okay? Any objection to what I said? No. Maybe you could say, but okay, I could integrate that, right? Why not? You give me the velocity, but I'm a good student, and I know that if I integrate the velocity, I get the coordinate back. So why can't I integrate that? Any suggestion? You see, to integrate this, you first have to solve the problem, right? Because you don't know. You need to know this as a function of time. So it's true that you have a relation that could be translated into a relation among the coordinates, but first you have to solve the problem. So that's why this is not a holonomic constraint, except for a very special case that we will discuss a little later. Okay, what else I should say? So we are going to stick to this holonomic constraint from now on, essentially, except some very special cases, because in that case, as I said, I'm able to crank in the generalized coordinates and forget about the constraint. But how about the work done by the constraint? You remember when we solved the problem with the sliding mass on top of the other, we worried a lot about the tension, and the tension was work done by the constraint, because the constraint was the string, and the movement of the string was the, okay? So if I'm going to forget about the constraints by using the generalized coordinates, I should also be careful that the forces of your constraints are not doing any work. Okay, and that's usually the case, but it's not always true. Okay, so I want to just say that before you start cranking in your Lagrangian, you want to be careful that the constraints are holonomic, and also the constraints are not doing any work. I'll come back that in a second, but just bear it in mind, okay? Any questions on this? You're too tired to, you only want me to stop. But just bear with me a little longer. Okay, I need one last concept, and then we start deriving these Lagrangian equations. And this is, I don't know if you have heard about this virtual displacement that I call delta Ri. So it's a small displacement, but it's not just a displacement. Is called virtual because is a change in the system configuration that is consistent with all the forces and the constraint frozen at the initial time. So why I get so excited about this? Because this is not so obvious. The system moves, so in general you have a displacement of the positions, right, that I indicate here. For instance, again, take a line and a little bob, a little mass on this that is constrained to stay on this line, okay? And this line is moving, for instance, is moving upward, okay? So if you look at the generic displacement of your system, in this case it's just very simple because you just have one R here, right? This thing moves up, okay? This moves like this, and this moves up. So in general, it will end up here, okay? Right? So if I indicate this as S, just one coordinate, this is delta S. Delta S with the D, the Latin D, is the real displacement of that point, particle. What is the virtual displacement? I said the virtual displacement is the movement of your coordinates, the displacement of your system, that is consistent with forces and the constraint, frozen at the initial time. So that means the delta S is just this, because I have to freeze the system, it's not moving. So this is delta S. Is that clear? So you have two kinds of, and we want to look at this one, okay? So this is the virtual one. And this, I don't know, the real one. And now I write this condition. So now I'm going to derive these Lagrange equations by using Newton's and using these displacements. This technique, this derivation is due to another guy that was called D'Alembert, a French guy at about the time of the French Revolution, so a little later than Newton. So let's consider a system that is at the equilibrium. Okay? So at the equilibrium means that all the forces are equal to, so it's at the equilibrium. So a system at the equilibrium means that it's not accelerating, right? And if it's not accelerating by Newton's law, that means that the forces are maybe like this. It's a zero vector. Okay, so I consider this situation, and if this is true, also this must be true, says D'Alembert, that I take the scalar product of all my forces times the virtual displacement of my system, this too must be equal to 0. Right? Simply because this is 0, so I'm just writing 0 equal to 0 in an interesting way. Okay? Now, the forces of my system can always be, they are made of two parts, right? You have the applied forces, so external forces, if you wish. So let's call it applied forces, and I put a little a on top here, right? Plus the forces coming from the constraints that unfortunately are still there, but I'm going to get rid of that. So this force has two components, the external force, the applied force, and the constraint force. Okay? So in other words, this thing really should be written as the sum of two pieces plus the terms that comes from this. And this is still 0. And now, as I said, I assume that my constraints are not doing any work, because what is this quantity? A force times a distance. That's what you call work. So as before, I said this should be equal to 0 because I want my constraint not to any work. No net work. So so maybe let's spend just a second on this. You see, you can for instance, let's go back. You remember Atwood machine? I hope so. It's just 48 hours ago, right? It was something, I don't know, like this with two masses. You remember, I hope. So what is the constraint here? Huh? Yeah, so the string itself is the constraint, and the forces of the constraints are the tension in the string, right? So is this Atwood machine satisfying this condition? Think about it. Because I'm saying the net, you see, is the sum of this that must go to 0. And you see that they go in the opposite direction. So it's true that it's doing some work, but it's exactly compensated by the other. So that's okay. So the Atwood machine can satisfy this condition. Of course, anytime the constraint is orthogonal, for instance, when I'm moving something on the plane, right, I have the constraint that gives me a perpendicular force, but is that force doing any work? Right? You know that in physics, if you are carrying a heavy luggage in this way, you are not doing any work. You know that, I mean, contrary to what you are thinking. Because, why? Right. Because there is a cosine there, right? And the value of that angle happened to be 0. So at the airport, when you carry that heavy luggage, actually you are not doing any work. Well, that's the definition. So you have situations like this or like this, okay? So you see, very often in your system, in fact, you are safe, and this term, this sum, you can neglect it, okay? So we are down to this simpler equation if you buy what I've said up to now. And now let me just, so this was a static situation. How can I turn this equation into a dynamical equation? Well, I started from this, that was the static equilibrium situation, but you know that if I write this as this, right? This is true because of Newton's law. This is the momentum, right? So and I take the dot. So if I replace this in there, still I have an identity that should be true. But now it's sort of a dynamical. So this was a static situation. Now it's dynamical because I have the velocity and the acceleration coming in, okay? And this equation, the fact that this is equal to 0, is called D'Alembert, as I said, I guess, D'Alembert principle. And as you see, it can be used, it's completely equivalent to Newton's law. But it's just written in this form and is useful for what we are going to do next. Okay? So that's D'Alembert principle, and is the first step in our derivation. It's nice because in a way it translates a dynamical problem into a statical one. And so it should be simpler. So now let me change variables. I want to get rid of all the constraints. So I change all my variables. Maybe I write it this way. So I have my variable, and I change them to the generalized coordinates, of which I have n. So I'm using, in a way, the constraint to get rid of some of these variables, and I want to write this in terms of my generalized coordinates. What happened to this variation if I change my variables? What happened? Right? Is this clear? Or the change in this variable, this displacement, once you change your variables, is equal to this partial derivative times the displacement of the new variable, and then you have to sum over all, depending whether this one depends on all of this, right? Or no? Have you ever done this? You have it's like before, right? You had, for instance, y that was x squared minus r squared, right? If you want to write dy as a function of this, how would you do that? This should be the partial derivative of y with respect to x, right? How much is that? So it's the partial derivative of y with respect to x times delta x. Actually, here it only depends on x, so you may as well take the total derivative. This you know. And this is just a generalization when you have more than just one variable, right? So you take the partial derivative in the various directions. So in fact, how much is this? How much is the derivative of the square root with respect to x? How much? Hmm? But you have a 2, no? Right? 2x divided by. Okay. So this is just the generalization. This is done when you only have one. So here is the case in which y depends only on one, right? So I have just y and then just one coordinate. If you generalize, here you have to take the partial derivative, and this is true.
Sir?
Yes.
When we say an object is at equilibrium?
When we say?
An object is at equilibrium?
I'm sorry, I did.
Equilibrium.
At the equilibrium, yes, sorry.
Then does it mean Fy is 0?
Yeah, because equilibrium means that it's there. So that means the acceleration is 0. And if the acceleration is 0,
Yeah, but I think Fy may not be 0, but the net force has to be 0 if an object has to
the
be
net force, yeah.
So we need just Fy.
No, I wrote the F. The first F was the total force. Then I decompose that. You have external forces and the constraint. And then I put the constraint equal to 0. Think about it. How about the velocity? You see, I need also the velocity. Actually, I'm going to need p. So what is the velocity? Is the total derivative of these coordinates with respect to time. And how do I write this in terms of the new coordinates? I have to act with this derivative on that expression, right? So that means this is the sum over k of delta, the partial derivative of I with respect to qk dot, because I'm taking the derivative, right? Plus, if this is the case, the explicit if this transformation explicitly depends on time, I also have a partial derivative with respect to time. So now I can rewrite these two terms in terms of my generalized coordinates, right? Let's start with the force. Huh? So the force is the force, and I only need to replace my displacement in terms of this. So this first term just gives me Fi A sub I times the things there that I wrote as a dr. So I think this is a I. Okay. And this quantity here, you see, now I have my variation in terms of generalized coordinate, so I may as well call this quantity like a q sub j, and you see this is a sort of generalized force, so this term looks nice. So here you have a sum qj delta qj, where this I call it the generalized force. How about the other term? Here I have to do some work. Are you following, or I'm a little worried about this? This is very trivial. I plug in this in here, and then I change the name of this term here. So I haven't done anything. But you must think of this as the generalized force that is, you see, is the scalar product of your force times the component of your initial coordinates along the direction of the new generalized coordinates. How about this term here? Let's write it explicitly. So you have a sum. So what is P dot? What is it? It's the dot of the momentum. So it's the mass times twice, right, is a mass. Maybe each particle has a different mass, so I call it mi. And then you have I twice dotted, like this, right? This is the P dot. And this is scalar product of this vector here times the position. And again, I have to change from my Ri to this Q. So I replace, here you have a sum over I and J, mi R dot I times, instead of this, I put my partial derivative of Ri dqj delta qj. It's just mathematics. Well, qj. And how about this term here? How can I rewrite this term? This blackboard is too small. I want to rewrite this term in such a way that looks a little bit with the velocity, right? You see, I have a second derivative times a partial derivative here. I mean, if you, yes? I want to pull out let's pull out one derivative, right? So dt of m I r dot I dri dqj, right? So this goes through, it hits this, and it gives me this, right? But this is not equal to this, because then this hits that. So I have to subtract a part that is what? Mi r dot I, the derivative, time derivative of the last piece. Right? You see that? I mean, this sum is equal to this term. Just this term here. Because I go inside this, and first I hit this, I get the acceleration. So this is this term, right? But then I also get this term here, but then I subtract this. So this difference is equal to this. And I have to massage this thing a little further, right? Because I'm not right there. Now look at this one. Look at this one. What is dvi with respect to dq dot j? Look at this equation. Okay. What is the partial derivative of the velocity that I wrote here with respect to q dot j? Remember, the partial derivatives only takes the explicit dependence of something. So what is that? It's just this this term here, right? So you see this term here is f, right? With respect to j, you're right. So you see this term here, the partial derivative of ri with respect to qj is equal to the derivative, the partial derivative of vi with respect to q dot. So this is dvi dq dot j. And how about this term here? Let's first switch. Okay, this I know I'm not allowed to do, but let me do it nevertheless. Let me switch the order of these two derivatives so that I have dqj, right, delta d of dtri. Okay, I mean, you are not allowed, but you are. And what is the, so what is the r I dt? Yeah? Yeah, use this. Is this r I d q k d, right? dqj sum q dot k. Right? So I can So here I have that, so I can put it inside. And I have the sum over k, dri, dqk, dqj, q dot k. Plus dri, dqj, dt. Okay? So, I mean, let me just one more step and then I stop because I see that I'm doing this. It's not a good day. How about this? I said I want to write everything here in terms of the velocity or derivative of the velocity. In particular, I want to write this as a kinetic term. So to do that, look at this. R dot I is what? It is also known as the velocity. So you see here, essentially you have Vi dot dvi dq dot j, right? And this quantity, well, if I write it as dq dot j is equal to 1/2 mi vi square, right? Take this derivative. You see, you take the 2 mi vi that is here, and then you hit with this derivative, the vi, and you get this. So mi is equal to this. So you see, from this term, I was able to extract something that looks what? What is this? This is T, the kinetic energy. And something similar, I can get it from here, right? Because what is this term here? Look at this. This term here, well, I write it the Arabic way. This term here, you see, is just the dqk of the vi. Look at what vi is, you see. So this is just dqk of the vi vector. So again, this term too can be written as dqj of 1/2 mi vi square. Right? So it looks like this one, but this is the partial derivative with respect to q dot, and here you have the partial derivative just with respect to q. That's the only difference. So let me stop here, but let me write what I did. I rewrote these two terms. So this one is just dqj, is the one down there, of the sum of mi, sum 1/2 mi vi squared. And the one upstairs I also have that one. dq dot j sum 1/2 mi vi squared minus this, okay? That minus that. And the other one, I just wrote it in this form here, okay? So if I collect all these terms, I write them here. So we said this thing here is the kinetic energy that I call T, as we did before. So you see that I have dt of the partial derivative of t with respect to qj, I guess, minus dt. So this is t, this is t. So I have d dq dot jt d dqj minus, right, minus the term with the force that I call it qj. All this stuff times dqj, this must vanish because of D'Alembert principle. Okay? So next time we start from here, but try to check, do it yourself, these steps. Just change your variables and check that you end up with this expression. But you see, we are we are almost there, because you see, from Newton law, here I have D'Alembert principle. I rewrote this in terms of the kinetic energy, and you see this looks very much what we used the other time, right? Because you see, this is looks a little bit like Lagrangian equation. The only thing that is missing here is the energy, the potential energy. I only have the kinetic energy. So we will have to work out that part there to get to the other term.